Are you able to see the slides?
No, sir.
No, sir.
No, sir.
No. Yes. Are you able to see the slides?
Yes, sir.
Okay, I'm changing over. Confirm changes. Yes.
Yes,
Yes,
sir.
sir. Yes, sir.
Okay. It's better to spend a minute on checking this rather than finish a lecture and make a fool of ourselves. Okay. Welcome to Department of Chemical Engineering, Banastali Vidya Peeth. We are on CHT 305 Chemical Technology, Silver Jubilee Lecture, lecture number 25. Landmark. Okay. So far in the petroleum industry, we have seen the upstream processes where we had a glance of the exploration and production of oil at the oil well. And then we came to the downstream processes in which we had a look at the physical processes and the chemical processes. In the physical processes, we saw desalting, dehydration, dehydration, atmospheric distillation. I told you to find out why it is called atmospheric distillation, even though the pressure is not atmospheric. Try to find out. It's also called topping column, vacuum distillation. Why is steam brought in? What is the purpose of using steam? Advantages. Solvent extraction. Those are things which you have to find out. Solvent extraction, propane deasphalting, methyl ethyl ketone dewaxing, blending. Then under chemical process, we have two categories, thermal and catalytic. I should put a tick mark here, take a tick. And thermal, we saw vis breaking, that is viscosity breaking, which is mild thermal process. Delayed coking is severe thermal process. Vis breaking is only for a few minutes. Delayed coking is for several hours. Flexi coking is the improvement of the coking process in which the coke produced also increases the output. Right. So it's a very interesting process, and new refineries are coming with flexi coker. And catalytic processes, we saw catalytic cracking, where our long chain hydrocarbon is smashed into small hydrocarbon, which have more market value. Catalytic reforming, since the crude does not contain much aromatics, the aromatics have a lot of octane value. So to increase the aromatics, we carry out catalytic reforming by which N-alkanes become cycloalkane, and further dehydrogenation results in formation of aromatics. Example, normal hexane becomes cyclohexane, and cyclohexane by dehydrogenation becomes benzene. Okay, so N-alkane to N-hexane, cyclohexane to benzene. Right, so that is the typical example of catalytic reforming. Then we saw alkylation, in which isobutane may be reacted with propylene or butylene to form 7 carbon or 8 carbon compound which have more octane number value. And alkylation may be done by sulfuric acid process or by hydrofluoric acid process. Sulfuric acid process requires cryogenic cooling, which is slightly on the expensive side, and hydrofluoric acid does not require. Of course, both are liquid catalysts. Hydrofluoric acid has its own problems of corrosion and very not a friendly acid, hydrofluoric acid, very active, and zeolite catalysts are thought getting in for the alkylation process. That leaves us with hydroprocessing, in which we have hydrotreating and hydrocracking, polymerization, isomerization, and catalytic dewaxing. Of course, remember, dewaxing can be done for the lube oil making using solvent also, methyl ethyl ketone or even propane as a solvent, and we are going to see catalytic dewaxing here. Okay, so over to the lecture today. We start with hydroprocessing. Hydroprocessing, as the name suggests, is a process which involves reaction with hydrogen, right? So I am carrying out my process in the presence of hydrogen. That has got the name hydroprocessing. Hydroprocessing may include hydrotreating and hydrocracking. So hydrotreating and hydrocracking. Hydrotreating, we have already seen a bit of it in hydrodesulfurization, where we had to remove the sulfur impurities before steam reforming of naphtha or natural gas, because sulfur is a poison for the nickel catalyst. So there we had to do desulfurization using in the presence of hydrogen. So hydrotreating and hydrocracking. They are fundamentally different because the objectives are different. We will see it shortly. Hydrotreating. The term hydrotreating is limited to just hydrogenation and hydrogenolysis reaction in which removal of heteroatoms. Heteroatoms are sulfur, nitrogen, oxygen. Remember, hydrocarbon means carbon and hydrogen. When in the hydrocarbon you have some sulfur compound, nitrogen compound, oxygen, they are called heteroatoms, right? Other than carbon and hydrogen, right? So is limited to hydrogenation, right? So unsaturated compounds get hydrogenated, right? And the major objective, hydrogenation of double bonds and aromatic rings. So remember, aromatic rings are also unsaturated, right? But their behavior is different. You know the properties of benzene, whether it undergoes addition or substitution. The benzene is a very unique, organic molecule because it has, 1.5 bond, right? Not a single bond or a double bond. That is why in the benzene ring you put a circle inside and not show the bonds as it is, because the bonds keep, the electrons in a decentralized way and they keep moving around. So you have studied the structure of benzene and its properties in the school. We'll not get back into it. Okay. The major objective of hydrotreating is protecting the downstream catalyst from hetero compounds. Remember, sulfur, nitrogen, and oxygen are probably undesirable for many of the catalysts we may be using for cracking, reforming, right? Alkylation. Such of them may not like the presence of sulfur, nitrogen, and oxygen. So the main purpose of hydrotreating is to protect the downstream catalyst from hetero compound. So you can say roughly, as soon as atmospheric distillation is done, all the fractions which come from the atmospheric distillation undergo hydrotreating. Look at this. Crude oil. This, remember, when I say crude oil, it is a desalted, dehydrated crude oil. So that is not shown, but you must be clear that it is desalted crude oil which enters the atmospheric column, where these fractions are coming. Some light gases like methane, ethane, then light naphtha, heavy naphtha, kerosene, gas oil, right? And the bottom of the atmospheric residue is the feed for vacuum distillation. In vacuum distillation, steam is also added. It is not shown, but make sure that there is an arrow for steam here, right? And you get a bottom from the vacuum column, which goes for residual conversion, and you get low sulfur fuel oil. This could be simply whiz breaking, etc. And the top one also undergoes hydrotreating, right? Or this also may be brought in to blend with this to form some variety of fuel oil. Fuel oil also, remember, there are many grades of fuel oil, right? Then this vacuum gas oil also will undergo hydrocracking, right? And this goes hydrocracking, not hydrotreating. So you can see that all the main fractions from the atmospheric column, the very first step is hydrotreatment. Then only other things like reforming, alkylation will happen, right? So this after hydrotreating, the vacuum gas oil after hydrotreating may undergo fluidized catalyst cracking. So to do FCC also you need a hydrotreating, because FCC catalyst will not tolerate the heteroatom. So hydrotreatment is almost mandatory for all the fraction from the atmospheric column and from the vacuum column. Right. Only exception here is I may get this vacuum gas oil directly to the hydrocracker. Right. So because in hydrocracking we are going to do cracking in the presence of hydrogen. So the objective is well taken. Okay. So come to this. In contrast, so the objective of hydro treating is protecting the downstream catalyst and prevent corrosion, etc. And the gasoline properties such as odor, color, stability, and corrosion, and protection of the environment. And hydrocracking, size reduction is done. Cracking means something big I am breaking into small, right? It's like, I have a big, glass vessel. I just drop it, it goes to pieces. So long hydrocarbon is like a big glass vessel, and in cracking, I smash it into pieces, right? So size reduction is the main objective, whereas in hydro treating, I'm not interested in breaking. I'm interested in quietly removing some atoms from here and there so that they don't create problem, right? Whereas in cracking, the aim is to break it into pieces, right? Hydrogenation occurs by addition of hydrogen, for example, to double bond or triple bond. Ethylene, acetylene, ethylene has got double bond, acetylene has got triple bond, and unsaturated hydrocarbons, which are called olefins, they are ready to undergo addition reaction because that is the chemistry, right? So they are ready to undergo addition reaction. Hydrogenolysis involves the breaking of, remember we use the word hydrogenolysis. What it means is there is a carbon-sulfur bond. I'll just break this carbon-sulfur bond so that the hydrogen will combine with sulfur to form hydrogen sulfide, or the carbon-nitrogen bond so that nitrogen will combine with hydrogen to form ammonia, etc. Right? So hydro treating is also sometimes called hydro purification. If it is focused on sulfur removal, you call it hydro desulfurization. If it is focused on nitrogen, we may call it hydro denitrogenation, etc. Right? So the first step in oil refining is the separation of crude into different boiling point fraction by the atmospheric distillation. That's what we saw in this figure, right? Desalted crude, atmospheric distillation, many fractions, they all undergo hydro treating and then subsequently go through reformer, alkylation, etc. And the bottom also of atmospheric column goes to vacuum distillation, in which here also hydro treatment is done before fluidized catalyst cracking, right? So the processes used, what are the catalysts used? Catalysts used are transition metal sulfides. This is the most preferred one. We will see it some more, right? We have seen this figure, right? Now we come to what are the catalysts used? They mainly depend upon the specific reaction and process requirement. In general, the catalyst for hydro-treating reaction, they have mixed oxide sulfides of COMO. COMO stands for cobalt molybdenum. NEMO is nickel molybdenum. NiW is nickel wolfram. W is for tungsten, right? Nickel wolfram, right? Supported on a high surface area carrier reaction, while NEMO sulfide catalysts are excellent in hydro denitrogenation. When I want to break the carbon-nitrogen bond and combine the nitrogen with the hydrogen to form ammonia, I use NEMO sulfide. And hydrogenation for also NEMO sulfide is a good catalyst. NiW, nickel wolfram, that is nickel tungsten, right? So remember, tungsten, the chemical formula is W, right? Nickel tungsten sulfide catalysts are very promising for hydrocracking and aromatic hydrogenation at low H2S concentration and conversion of alkylated dibenzothiazine. Although the high cost of these catalysts makes industrial application less attractive. Noble metal catalysts like palladium, PD is palladium, and platinum or platinum, they have gained increasing attention because they are very good in hydrogenation. Platinum or palladium is very good for hydrogenation, and however, these catalysts are sensitive toward poisoning by sulfur compounds. Right. Interestingly, COW, that is cobalt tungsten sulfide catalyst. Of course, we have seen nickel tungsten is a good promising, but cobalt tungsten sulfide catalyst is somehow not found to be a good combination for applying in industrial hydro treating. In general, the specification of the feed, what the feed contains, and the desired product will determine which catalyst or combination of catalysts will be used. Remember, we have to see whether we are removing sulfur, nitrogen, or oxygen, and choose a catalyst or a mix of catalysts accordingly. In hydrotreating, the following terms are used, referring to the heteroatom removal. Sulfur, nitrogen, oxygen, and M. It may be any other metal also. Hydrodesulfurization, HDS. Hydrodenitrogenation, HDN. Hydrodeoxygenation, HDO. And hydrometal demetallization, HDM. These are all abbreviations for removal of sulfur, nitrogen, oxygen, and metal. Hydrodemetallization. Now, we'll see a figure. Before that, it shows the simplified flow scheme of the hydrotreating process involving a trickle bed reactor. This is a type of reactor which you'll be studying in the reaction engineering course. So we'll not get into it. But make a note to find details of trickle bed reactor. The feed is mixed with fresh and recycled hydrogen and preheated by heat exchange with the reactor effluent. Because the reactor effluent is hot and the raw material is cold, so I exchange heat for heat exchanger economy, right? This reduces the fuel consumption of the furnace. The reactor usually contains several catalyst beds with the intermediate cooling by hydrogen injection quench. Right, I'm not putting all the hydrogen in one place. I'll distribute the hydrogen so that it acts as a quench also to take away the heat. In the reactor, the sulfur and nitrogen compounds are converted to hydrogen sulfide and ammonia. The effluent is cooled and sent to a hot high pressure HP separator where hydrogen is separated for recycle. And the liquid from the high pressure separator is let down in pressure. Pressure is reduced and sent to the low pressure separator and then to the product stripper. Product stripper because my product has got several hydrocarbons, and by stripping, I'll be able to get the different fractions. So let's see the figure. Remember, the input is feed. Feed is the fraction which is coming from the atmospheric column. It could be any of this, right? Hydrogen is also required. That is why it is known as hydrotreating. So hydrogen and the feed, they get heat exchange here and then go to a furnace, get heated, and then enter the reactor, where the reactor is filled with a catalyst. If it is sulfur removal, you know what catalyst is required. If it is nitrogen removal, what catalyst is required. So catalyst is there in packed out here, and some hydrogen is also injected into different parts of the layers of the catalyst to pull out the heat. So this hydrogen is cold, and the cold hydrogen takes away the heat within the reactor, right? So that the reactor heat economy is taken care. So the products come through a heat exchanger where the hot product is heating the fresh feed, and then it goes to the high pressure separator, and from the high pressure separator it goes to the low pressure separator. From here the hydrogen is separated and it is recycled back. And still remember, the gases contain both hydrogen and hydrogen sulfide, and there are many solvents for absorbing hydrogen sulfide like monoethanolamine, diethanolamine, potassium carbonate, etc. So some solvent is used in which the H2S is absorbed, and by boiling the solvent, I will remove the H2S and the hydrogen is recycled. And from the low pressure separator, I take it to a stripper. Stripper means where I am having hydrocarbons with different boiling point. It's like a distillation column. So here I get my different products, some naphtha, some product, and some gas, which may be used for fuel purpose or something, right? And depending upon the feed, look at the temperatures. If my feed is naphtha, my temperature is 590 to 650, pressure is 15 to 40, and hydrogen to hydrocarbon feed is 0.1 to 0.3, and WHSV, right, is 2000 to 5000, right? And here gas oil, this may be, remember, this could be gas oil or naphtha, right? So gas oil may be 600 to 670, pressure is more 40 to 100, and hydrogen carbon ratio is 0.15 to 0.3, and WHSV, right, is 500 to 3000. Okay. Remember the unit, kg feed in terms of meter cube H. Then comes hydrocracking. So already you know that hydrocracking, the objective is to do, hydrocracking is same as cracking or fluidized catalytic cracking you have studied, except that we do the cracking in the presence of hydrogen. That's all. What is the objective? See, when I do only cracking, I may be producing some unsaturated compound also on aromatics, right? But when I do hydrocracking, there will be no unsaturation because any ethylene, propylene formed in cracking will all get saturated by the hydrogen present, and any aromatics will also get hydrogenated, and so my output will be mostly mostly? It will be saturated product, no unsaturation at all. Hydrocracking is a catalytic oil refinery process of growing importance. Most modern refineries are hydrocrackers because remember, hydrocracking is capable of, tackling the kachara of the vacuum distillation and make useful product. So by hydrocracking, I am bringing into the diesel portfolio. Whether otherwise it would have been a useless fuel oil for me, but my hydrocracking has ensured that my output from the hydrocracker is giving me some more gasoline, kerosene, and diesel. That's a big deal. Okay. So hydrocracking improves the yield of kerosene, diesel, and gasoline, and the increasing need for production of clean fuels. I want clean fuels has also had a significant impact. As the name implies, hydrocracking involves the cracking of a fraction into lighter product in the presence of hydrogen. In the presence of hydrogen. This is a difference between the catalytic cracking and hydrocracking. Both have the same purpose, and catalytic cracking is doing in the hydrogen is not required, but in hydrocracking, presence of hydrogen is a must. This distinguishes the process from FCC, which does not have hydrogen in the feed. And from the hydrotreating process, virtually no CC bond breaking takes place, right? So saturation comes. Hydrocracking is a very versatile and flexible process that can be aimed at the production of naphtha or at the production of middle distillate, namely jet fuel and diesel fuel. And although at first sight, it might be expected that hydrocracking competes with FCC, this is certainly not the case. The processes are complementary. See, FCC and catalytic hydrocracking may look the same, but they are not competing with each other. They supplement each other or complement each other so that more output of the lighter fractions is got. FCC takes the more easily cracked alkane-rich atmospheric and vacuum gas oil as feedstock, while the hydrocracker uses more aromatic feeds such as FCC cycle oil and distillates from thermal cracking process, although it takes heavy atmospheric and vacuum gas oil and de-asphalted oil. Right. So hydrocracking, see, the FCC is taking, the very neatly produced. Just see, what is the FCC is taking? Maybe any of these fraction or even this vacuum gas oil, right? Whereas hydrocracking is capable of taking much more, uh, uh, heavier fractions of the distillate. Okay, that is the main difference. Okay. And coming to hydrocracking is a combination of hydrogenation and catalytic cracking. So there are two things simultaneously happening. There is a catalytic cracking happens, a big hydrocarbon is getting smashed into smaller hydrocarbons, and simultaneously hydrogenation is happening so that the unsaturated compound are all saturated, right? The former reaction is exothermic, hydrogenation is exothermic, and the catalytic cracking is endothermic. Since the heat required for cracking is less than the heat released by hydrogenation, the overall process is exothermic, right? So for cracking, I don't need too much of heat, but my hydrogenation releases a lot of heat. So overall, my hydrocracking is a exothermic process, right? Dehydrogenation, hydrogenation, and heteroatom removal require a hydrogenation catalyst, while the actual catalytic cracking reaction proceeds by a carbenium ion, that is a C plus ion, and therefore requires an acidic catalyst. Various catalysts are in use, as in hydrotreating. Mixed metal sulfides are used for hydrogenation function. Noble metals are also used, like platinum, palladium. The additional cracking function is fulfilled by a more acidic carrier, like maybe silica alumina or lately zeolites, right? Nitrogen compounds, many of them are basic, present in the feed, play an important role in hydrocracking because they absorb on the acidic catalyst and thus inhibit the cracking reaction. Therefore, in most processes, hydro-denitrogenation is necessary as a first step before the hydrocracking. Please understand this carefully, that you see, if I don't do hydro-denitrogenation before hydrocracking, my nitrogen present may play mischief with the catalyst in hydrocracking. So I would prefer that we do hydro-denitrogenation before the actual hydrocracking is done. Okay. There are many configurations which may be single stage, two stage, or series flow hydrocracking. We'll see them. In the design of a hydrocracking process, hydrogenation and cracking reactions have to be balanced carefully. Single stage 1 through hydrocracking is similar to hydrotreating, except for different catalysts and more severe process conditions. It's the simplest configuration of the hydrocracking process with the lowest investment cost. Apart from producing middle distillate, this process produces naphtha. It can be used, for example, feed to a catalytic reforming unit or a naphtha cracker for ethene, that is ethylene production. The conversion of the feedstock is not complete, so still some material present with molecular weight range as the feedstock, but the unconverted product is highly saturated and free of feed contaminant. It has been hydrotreated and thus is an excellent feedstock for other processes such as FCC and lube oil production. So remember, hydrocracking is also very useful in the production of lube oil, and the process is optimized for hydrogenation rather than for cracking. Let's see the single stage, two stage, and series flow. In single stage, the feed is entering, right? Remember, HC is hydrotreating, HC is hydrocracking. So this catalyst partly does hydrotreating and partly does hydrocracking, and from there it goes to a fractionator where different fractions are removed. This is single stage or one through. In two stage, I have a hydrotreater, a hydrocracker separate, and a fractionator. Here both are integrated. So first I do hydrotreating, and then, right, that goes for fractionation, and from the fractionator, the bottom product is brought for hydrocracking, and then that also goes for fractionation. Very interesting, right? And in the third series flow, I have hydrocracking, these both look alike, but just see the difference, right? Here, the feed is coming, hydro treatment is done, and the bottom straight away goes to the fractionator, right? It is not entering the hydrocracker. Whereas in series flow, the hydro-treated output is getting into the hydrocracker, and from here it goes into the fractionator, and the bottom product is again recycled. Okay, so you just see there is a big difference between single stage, two stage, and series flow. Next comes olefin polymerization. I'm using the word olefin polymerization because remember, in fluidized catalytic cracking, when I do FCC, small quantities of ethylene, propylene are produced. I cannot stop it. If I have done hydrocracking, then my ethylene, propylene would have got saturated into ethane, propane, right? But if I do normal fluidized catalytic cracking, I am getting some ethylene and propylene, which are not desirable in the petrol, because the unsaturated hydrocarbon, they will form gum-like product in the gasoline and can block the engine, right? So olefins are not desired in the gasoline. So what do? I do polymerization of the olefin, right? So remember, in normal sense, polymerization means monomers coming in, monomers joining in large numbers to form a long size polymer. But in the petroleum refining, polymerization is just about a dimerization or a trimerization, right? So just two molecules combine or three molecules combine to form a dimer trimer, right? Very limited polymerization, right? But not large scale, long chain, right? Olefin polymerization yields polymer gasoline, which is primarily carried out to obtain polymers with good octane number, right? So the octane number of the polymer gasoline product is not greater than the octane number of the product produced from reforming and alkylation. So by reforming and alkylation, I'm having good octane number, but if I do olefin polymerization, I will get, another equally good octane number, right? Comparatively, instead, comparatively poor quality product is obtained, but for the sake of enhancing octane number, still polymerization is carried out, right? So polymerization is not a very fancy thing, but for the sake of pushing the octane number, we do this olefin polymerization. On the other hand, polymer gasoline has more vapor pressure than the corresponding alkylation product. Therefore, in both ways, polymer gasoline product quality is lower than that obtained from the alkylation unit. So the gasoline blend I get from alkylation is far superior than the gasoline blend I will get from the polymerization. So you can see that alkylation is superior to polymerization, but still I don't want olefin, so I'll do olefin polymerization, right? Typical feedstock may be C3 and C4. C3 and C4 olefin means C3 is propylene, C4 may be butylene, right? They are got from the catalytic cracking. Remember, catalytic cracking, I am not using the word hydrocracking, because if you do hydrocracking, there is no olefin in the product at all, right? So what we are doing is normal fluidized catalytic cracking, where I am having small quantities of propylene and butylene also, right? The end product from polymerization is a dimer or a trimer of the olefin. So when two propylene combine, you form a 6-carbon compound. When two C4 combine, you form a C8 compound, dimer, right? So at the most, polymerization is limited to a dimer or a trimer. The reaction mechanism is interesting. We are looking at the basic steps. I have not shown the chemistry behind this because you can read it out separately. First, the carbonium ion is formed, That is step 1. The olefin reacts with the acid catalyst to yield a carbonium ion. And in the next step, an addition reaction takes place. The carbonium ion reacts with the olefin to generate another intermediate carbonium ion. And the regeneration, the intermediate carbonium ion convert to the dimer and generate the proton back on the catalyst surface. Right. So catalyst is typically acidic because the carbonium ion is to be generated. Carbonium or carbenium, both mean the same. Carbenium is a more later usage. Carbonium is a older use of the same C plus, right, ion. Okay. And the last step is isomerization, where a straight chain proton substituted olefin convert into isomeric carbonium ion. Catalyst used is the acid catalyst, could be sulfuric acid, temperature 150 to 2 degree, 220 degrees C. Too high a temperature will give. See there, when the too long a polymer is formed, you form tar-like deposits, right? And pressure use is 25 to 100. So the temperature suggested is 150 to 220, because beyond that, tar-like deposits end up. Excessive polymerization will not be good. You want a dimer-trimer, that's all. This is the flow sheet of the polymerization process. You can see that C3, C4, olefin feed, propylene, butylene, right? And some caustic is added because the catalyst is sulfuric acid. So I'll have to do a caustic wash so that the sulfuric acid is neutralized, right? So you can see they are mixed thoroughly and then goes for a caustic wash, right? So dimer trimer has formed, and then some water wash is done, and then the separation sequence is happening here, right? Cooling reactor, cooling water, and then I have a depropanizer where the propane is removed, right? And debutanizer where my butane is removed, and my heavier one, this bottom product is my polymer gasoline, right? And I add some hydrogen so that there is no unsaturation at all, right? So this is the scheme of olefin polymerization. Keep in mind that we are not looking at a long chain polymerization. We are just interested in just a dimer trimer. Then comes isomerization. Very interesting. See, remember, butane and isobutane, they have the same formula. You know the funda of isomers, right? Same molecular formula, but different structure. Different structure. So what's happening is the basic principle of isomerization is straight chain alkane to side chain paraffin. Look at this. N-pentane has octane number of 61.7, normal pentane. That is CH3, CH2, 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 CH3, 5 carbon pentane. Octane number is 61.7, whereas isopentane has octane number of 92.3. Fantastic. So my iso compounds have more octane number than normal pentane, normal alkane. Isoalkane has more octane number than normal alkane. That's why I want to do isomerization. I don't want pentane in my product, I want isopentane. I don't want butane, I want isobutane, right? Usually light naphtha is used as a feedstock, platinum-based catalysts are used, and aluminum chloride is used as a promoter for the catalyst, and during reaction, part of the aluminum chloride gets converted to HCl. Remember, we are using the word catalyst, but some aluminum chloride end up becoming HCl, and therefore completely dry condition should be maintained to avoid catalyst deactivation and corrosion. Catalytic reaction takes place in the presence of hydrogen to suppress coke formation. So I ensure some hydrogen present so that carbon formation. Coke means, carbon, right? Carbon dust formation. Now, let's look at the flow sheet of isomerization, right? I have my N-paraffin feed, my normal paraffin, say pentane or butane, normal pentane. Then it gets dried. Remember, In the wet condition, aluminum chloride may end up becoming HCl. Dry condition must be maintained. So a dryer, right, and then go to the reactor, right, and what else we said that typically these take place in the presence of hydrogen, right? So go to, this is your reactor. Then I do my aluminum chloride recovery because that is a catalyst, aluminum chloride, right? And some aluminum chloride is lost, which I have to do makeup and recycle the catalyst back to the reactor, and the recovered aluminum chloride, right? Some HCl has formed, the aluminum chloride has come, but some HCl formed, goes to a flash drum in which the HCl removal is done, HCl stripper. So HCl is coming out, and then given a caustic wash. Because of the acidic condition, a caustic wash is done, right? And then fractionation, where I get the isomerized product, and the bottom from here is also recycled back. Okay, so make a note, isopentane, octane number 92.3 and normal pentane 61.7. Just look up for normal butane and isobutane, same way, right? So the iso compounds have more octane number. So in my refinery, I would like to have a isomerization unit so that wherever I can catch normal pentane and butane, I will convert them into isobutane and isopentane. And remember, isobutane is also required for the alkylation reaction, because alkylation reaction, recollect from the previous lecture, alkylation is isobutane is reacting with propylene or butylene, right, to form a 6 carbon or a 7 carbon or 8 carbon product. Okay, so isomerization is done. Then comes catalytic dewaxing. We have already seen. Now, why we should do catalytic dewaxing? Catalytic dewaxing is a process that ensures that the product like the diesel or liquid at the specific temperature. Remember, if wax is present in the diesel, just imagine some wax forming hydrocarbons are present in cold weather, that will freeze and will spoil the diesel, right? So the diesel will not flow, right? And diesel must be liquid at the specific temperature range in which they have to be used in order to meet the cold flow requirement. Remember, very cold, weather, Arctics and all, how will you run it? So if my diesel has got wax forming substances, my diesel will be finished, right? It will not flow because the wax now will form solid lump and choke the diesel, right? All diesel contains certain amount of wax component. They are N-paraffins, right? So wax components are typically N-paraffins. Remember the lube oil, right? We had seen some carbon range is what is suitable for making the lubricating oil and wax, etc. They are usually considered an important constituent because of their high cetane value. N-paraffin is good. It has a good cetane value, but it has a nuisance value also. Diesel requires a high cetane value, but my N-paraffin, if it forms wax, I should avoid it. So wax in the fuel is normally liquid, but when the diesel gets cold, the wax begins to crystallize. And when the temperature gets even lower, there will often be enough wax crystals to block the fuel filter, and the lines and the engine will simply stop running. This is particularly a problem in colder climate. Dewaxing is also essential in producing renewable diesel from biomaterial that contain fatty acids, as these will contain substantial quantities of waxy paraffin. So the biodiesel also, catalytic dewaxing must be done, right? So we must ensure that N-paraffins after hydrotreating and can sometimes remain solid even at plus 20 degrees centigrade. So conventional dewaxing catalysts are designed to improve the cold flow properties by shortening the chain length. See, remember, whatever catalyst I use will break my paraffin into smaller paraffin, right? The chain length will be reduced, either by pure cracking or by a combination of cracking and isomerization or both N and isoparaffin. Because of conventional dewaxing catalyst significant cracking functionality, see, most of the catalysts used for dewaxing, they were actually doing the job of cracking, breaking the paraffin into smaller one, right? This is what gives the yield loss and performance problem in winter conditions. Now, dewaxing by isomerization, on the other hand, ensures that the number of carbon atoms in the hydrocarbon remain the same. Remember, in isomerization, the carbon atom, they do not reduce. Only say mm, butane, normal butane becomes isobutane. Normal pentane becomes isobutane. So the number of carbon remains the same. So if I do dewaxing by isomerization, my carbon atoms are ensured, right? So I would prefer my dewaxing to be done using an isomerization route rather than a cracking route, right? See, number of carbon atoms 18, boiling point 316, melting point 28 degrees centigrade. Now, if this hydrocarbon goes through isomerization, my carbon atom remains 18, and my boiling point is a little less because the iso has property different from the normal chain, right? Normal chain is stiff, whereas the iso is a bent branched one. So boiling point is lower. Melting point is 28 here, whereas melting point is far less, minus 6 degrees. Right? So my normal alkane has become a branch to an iso. Carbon atoms remain the same. But if I add hydrogen and crack, then I form something big and something small, in which one has got 14, other has got two four, remaining four. 1, 2, 3, 4 carbon atoms. Boiling point is far less, 254. Melting point is 6 degrees. So you can see that my dewaxing should be done preferably by isomerization rather than by cracking. This TK930D wax, this is a Halder Topsy special catalyst, is based on zeolite structure featuring selected base metals that are not sensitive to sulfur, nitrogen, and hydrogen sulfide and ammonia present in sour operating environment. In fact, the base metals used in this catalyst ensure exceptional hydrogenation activity in such conditions, supporting hydrodesulfurization, hydrodenitrogenation, and hydrodearomatization reaction. The zeolite structure acts as a molecular sieve that only allows certain reactant molecules, the long N-paraffin, to pass through and take part in the isomerization reaction. Right? And it will not alter the others. The new catalyst, that is the zeolite catalyst by Halder Topsy, enables refiners to meet cold flow property regulation with the highest possible yield. Okay, so catalytic dewaxing. This is the flow sheet for it. So this hydrogen is present, right? So it is done in the presence of hydrogen. So you can see some, of course, some cracking is happening. The dewaxing catalyst, right? So what else? HDS is sulfur, diesel with large quantity of sulfur. ULSD is ultra low sulfur diesel, right? I think this should be HSD, high sulfur diesel, may not be HDS, HSD it should be, right? High sulfur diesel, this is ultra low sulfur diesel. So I am converting high sulfur diesel into ultra low sulfur diesel by my catalytic dewaxing process, right? Yes. So various removal is done to it is catalytic dewaxing. I could have used a solvent like MEK also, but catalytic dewaxing is catching up in a big way. So to wind up our discussion on the downstream processes in the refinery, we have seen the physical processes and chemical processes. In the physical process, we saw desalting, dehydration, atmospheric distillation, vacuum distillation, solvent extraction with examples of propane deasphalting, ethyl ethyl ketone dewaxing, and blending. See, blending is nothing but I have a alkylate product, I have a reformer product, I have a hydrocracker product, I have a FCC product, I have the straight run product, and I do blending the way I want to have my required grade of petrol. Okay, and in the chemical process, we had thermal and catalytic, and in thermal, we saw vis breaking, delayed cooking, and flexi cooking, and in catalytic, we saw catalytic cracking, catalytic reforming, alkylation, hydroprocessing, where hydrotreating and hydrotreating cracking we saw, polymerization, isomerization, and catalytic waxing. Now that ends the downstream process, but one very important topic in refinery is corrosion. Corrosion and its control. So this is a reference, you can go through it, but I'll just give a quick summary of it. Corrosion is a common problem because we are handling thousands of millions, thousands of gallons of crude oil, and it contains sulfur and other impurities. So corrosion is a problem, and the conditions of refining are different, right? Very severe temperature, pressure, pH, moisture, etc. Corrosive component is diverse in the refining process system. Various corrosion problems arise, and we have various methods of tackling it. There's a chemical dosing, inhibitor dosing, water dosing, suitable desalting, using proper materials, and maintaining appropriate operating process parameter to minimize the corrosion effect economically. To minimize the corrosion effects economically, corrosion effects economically are recommended. Now, if you look at this table, these are various parts of the refinery where these are the considered the corrosive component. For example, in the tank, I have HCl, HGS, dissolved oxygen. Heat exchangers, HCl, HGS. HGS furnace, H2S and sulfur compound. Flash zone, where the pressure reduction is done, H2S, Z compound, S compound, sulfur compound. Middle zone, H2S. Top zone, HCl and water. And tower overhead. If you have a look at it, you will see H2S and HCl seem to be the big villains all along. In almost everywhere, HCl and H2S is playing the dirty game for corrosion. So how do we go about it? Right, from the above table, HCl and HCl, H2S and HCl and other chlorine sulfur compound. Carbon steel is the most common material of construction because um, uh, it's the common material of construction for refinery equipment. This carbon steel is corroded because of presence of water and oxygen, mainly in the surface. This can be lessened by eliminating the water from the surface of the metal by means of a protective barrier or coating. So I give a coating on the equipment that will prevent water from touching the equipment. Right. Other types of atmospheric corrosion are corrosion under insulation, fireproofing, corrosion of pipeline, corrosion of structures, and cooling water corrosion. Preventive action. How do I minimize corrosion? Desalting. You have already discussed it in the first step in downstream operation, so it will not be repeated. The other two are chemical dosing by many methods and material selection. We'll just see what they are. Chemical dosing may be by emulsion breakers, caustic soda injection, neutralized ammonia injection, corrosion inhibitor, water dosing. A brief discussion of the above 5 methods. Emulsion breakers, they are by adding specialized emulsion breakers or chemicals, right? We can remove the unwanted substances, right? They also assist the desalting operation. It will enhance the speed of separation, but will assist the residence time, improve solids, etc. And these are added in very small quantities, just a few ppm to 100 ppm. Overdosing must be avoided because it incurs the risk of reversing the emulsion. Right? Emulsion means the impurities gather and come as a foam-like. Right? Then caustic soda injection. This is a very commonly used one. Crude contains water and inorganic salts, sodium chloride, magnesium chloride, calcium chloride, and hydrolysis of calcium and magnesium chloride occurs when crude oil is heated in the preheat exchangers and fired heater, furnace, right? So the hydrolysis of gaseous HCl. Now, you see, what is being done is calcium chloride reacts with water to form calcium hydroxide and HCl. Magnesium chloride reacts with water to form magnesium hydroxide and HCl. So my NaCl and H2O will form NaOH and HCl, right? So at high temperatures, 480, right? Furnace outlet crude temperatures typically they range from 360 to 380 degrees centigrade, in which sodium chloride is mostly stable, but most magnesium chloride and calcium chloride are hydrolyzed, right? At higher temperature only, sodium chloride also comes up with water to form a little bit of caustic soda, right? So you can see that what is done is this can be prevented by adding caustic, right? So by adding caustic soda, and I am neutralizing the HCl, right? So you know the reaction of sodium HCl and caustic soda will form sodium chloride, right? More stable NaCl and caustic soda. So that we know desalting will remove the sodium chloride, right? Caustic soda also reacts with any HCl vapor and produces more stable NaCl and accumulates in the distillation column bottom rather than the overhead steam. So caustic injection is one way of taking care of the corrosion problem. Then ammonia injection. Ammonia may combine with HCl to form ammonium chloride. This is another way of tackling the corrosion problem. Remember, HCl, H2S were villain. So here, caustic injection, I am using caustic soda to catch the HCl and form sodium chloride. And ammonia is catching up with HCl to form ammonium chloride, right? So this is another possibility. Then I add what chemicals known as corrosion inhibitors. Corrosion inhibitors are small chemicals which are referred as filmers, which means they will form a thin film it's like a bodyguard, right? So it gives a protective layer to the equipment so that this will get affected and the material of the equipment will get saved, right? So this is also added in very small quantities, 12 ppm, etc., right? So overdosing is to be avoided. Water dosing, to an extent, even water helps you in removing the corrosion problem. Water is added with a crude in desalter for ensuring proper salt separation. So to do the desalting, we are actively adding water. That is to prevent the corrosion. And demineralized water is also dosed in the overhead system to scrub off the ammonium chloride, etc. So water dosing is another option. And that is about it. So we have seen the 5 methods: emulsion breakers, caustic soda, neutralizer, corrosion inhibitors, and water dosing. Corrosion inhibitors are specialized chemicals, okay, and water dosing. Then material of selection, right? So my heat exchangers and the refinery equipment, my materials may be carbon steel, carbon molybdenum, chromium, molybdenum alloy steels, martenset and ferritic chromium stainless steels. These are all structure and properties of materials, gives you different potential to these alloys, and authentic chromium nickel stainless steel, copper alloys like brass, bronze, cupro nickel, nickel alloys, nickel, monel, inconel, incolloy, aluminum alloys, titanium. I have a whole lot of combinations for choosing my material. And a commonly used material for the refinery, we are just seeing, for HCl, organic and inorganic chloride, Monel is generally resistant to corrosion by weak HCl. Monel is the name of an alloy, right? You can see the properties of it, and monel cladding is used at the top portion of crude distillation column. Typical corrosion rate for monel is 0.002 inch per year. And H2S, organic sulfur, etc., straight chromium steel is the preferred one. It contains 12% chromium, and those with half to 1% of molybdenum, such as 5, 7, 9% of chromium, have good resistance to this corrosion. So, chromium steel, when to tackle H2S. Carbon dioxide, again, monal, etc., take care. Organic acids, copper alloys, have more resistance than steel, so copper alloys. And nitrogen compound, stainless steel or plastic laying may be required for protection against corrosion due to nitrogen compound. And also remember, to minimize the corrosion, determine the crude nature, especially crude, how much salt is there, sulfur content, acid number. Remember the crude assay we saw in the very first lecture. Those will help you in deciding how to choose the corrosion method, maintain suitable operating process parameter, temperature, pressure, excursions are to be avoided, maintain the operating conditions strictly, and apply the chemical dosing without interruption, ensure effective crude desalting and proper material selection, effective corrosion measurement tools should be installed in proper location, and corrosion trend should be analyzed to take necessary preventive action. One more issue in the refinery is environmental regulation, right? The trend of stricter environmental regulation started in the 70s, and now environmental regulations are very strictly to be followed, no excuses. Reduce particulate matter emission, for example, better cyclones and high efficiency electrostatic precipitators are added to the FCC unit, because in the FCC, coke dust formation may happen, and these particulate will have to be controlled. So electrostatic precipitators and cyclones are brought in and reduce sulfur oxide and nitrogen oxide emission. This sulfur oxide emission from FCC is reduced by hydrotreating of the FCC feed and use of SOX transfer additives. And for removal of sulfur oxides and nitrogen oxide from other sources, flue gas scrubbing may be used. At some plant, limitations of on the nitric oxide may require addition of post-combustion nitric oxide removal on boilers and heaters, for example, by selective catalytic reduction, SCR. Improved energy efficiency and reduced carbon dioxide emission. These are the environmental issues, right? And reformulated gasoline. The need for higher octane in reformulated gasoline combined with upper limits on gasoline component has a great impact on refinery operation. See, we can't go on increasing the octane number. We'll have to have some end to it, right? And low sulfur fuel. Recent regulations limit the sulfur content of gasoline and diesel fuel. They are stimulating the installation of a large number of new hydrotreaters, like hydrotreatment we have just seen, right? Otherwise, your petrol and diesel cannot carry sulfur particles. It will let out sulfur dioxide as the emission, right? So this is to be looked into. Now, refinery types. A topping refinery, the simplest refinery, it will only split the crude oil into main components. The amount of fuel oil produced is large, 3%. 3% is, see, out of the total refinery, say 100 refineries, just 3 refineries may be topping, in which say only atmospheric distillation is done. And a hydro skimming is, it has got a catalytic reforming in addition to atmospheric distillation. Roughly 9% of the refineries in the world are hydro skimming. 3% are topping. Topping means only atmospheric column. And in hydro skimming, atmospheric column and a catalytic reforming unit, right? And a hydro treating unit also for removal of sulfur. Remember, reforming cannot be done without hydro treating. Otherwise, the reformer catalyst will go for a 6, right? So 9% of the refineries in the world are hydro skimming. Third one is a cracking refinery. Roughly 50% of the refineries in the world are cracking refineries. In such a refinery, vacuum distillation is definitely there, atmospheric and vacuum distillation. And I have FCC or hydrocracking, right? and to produce more gasoline and gas oil, and the light alkene from the FCC undergo alkylation. So you can see the cracking refinery has got atmospheric column, vacuum column, FCC or hydrocracking, and also alkylation, right? With isobutane to produce alkylate. There is still some fuel oil. So 50% of the refineries in the world are cracking refineries. And the last one is the most advanced refinery. It's a coking refinery. Remember all that, with breaking, delayed coking and flexi coking. So 37% of the refineries in the world are the coking refinery. And most of the fuel oil is upgraded to light product. It has some kind of a coker to convert the vacuum residue. Delayed coking is employed most often, or flexi coking. Next comes the feel of the topic, refinery petrochemical integration. See, right now we have done what happens in a refinery, right? Now comes the next. From refinery, you know, the gasoline, petrol, diesel, kerosene, they all go as fuel to the market. But there are so many other chemicals which go for petrochemical plant. So there is a need for refinery petrochemical integration, because in future the petroleum based fuels, people switch over to hydrogen or electric cars. So what will you do with the product producing petrol, diesel and kerosene, right? So I will have to use my refinery to make large number of organic chemicals, which are petrochemicals, means chemicals using which are based on petroleum raw material, right? Petro FCC, right? So especially in the Middle and Far East, this is what FCC process has been developed to Petro FCC. The catalytic cracking is mainly with the intention of, developing the petrochemical industry. The phasing out of the idea of increasing the octane number of gasoline by increasing the aromatic content is changing the role of catalytic reformer. So, see, how long I'll keep producing more and more benzene, toluene, toluene? I mean, there is no end to increasing the octane number. So it is time I stop using the benzene, toluene, xylene for making whole lot of aromatic chemicals, right? So benzene, toluene, xylene, I don't want to block it for adding to the gasoline for increasing the octane number. I would rather use as raw material benzene, toluene, xylene for making petrochemicals. In addition, the installation of gasification units processes vacuum residue open the way for production of a variety of petrochemicals from syngas, right? Syngas, you know, carbon monoxide and hydrogen, right? So you could see this a report on this, right? I've just given the reference. Just have a look at it from 2010, 2020. The green line, red line is the petrochemical product rising, and the green one are almost reaching a plateau. Refinery products have reached the saturation. So from 2020 to 2040, more or less the refinery product is remaining at the same level, whereas the petrochemicals are booming, 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 booming. Right. So this graph is got from this reference. This is to tell you that the refinery is becoming stale. It is a petrochemical which is now booming. So the time for us to pick up, how do I do it? So the FCC coker makes me propylene. From the reformer, I get benzene, toluene, xylene, and this benzene, toluene, xylene is now my petrochemical product, and I get ethylene. From ethylene, I also get ethylene, propylene, butadiene, and other fuels. So this is a way of refinery to petrochemical integration scenario, right? And so our next topic is going to be petrochemicals, which we will start tomorrow. So thank you all. Thank you. So that is the end of refining. Remember, in the last 4 lectures, right, we started with upstream, production and exploration. Then we moved into downstream. We have exhausted the physical processes and chemical processes, right? So by now, the refining industry, petroleum industry is at your fingertips. And now comes the next interesting aspect of petrochemicals, which will start tomorrow. Okay, so that's it, and thank you all. Have a great day. Wonderful Sunday to you. Okay, bye.